Welcome back to the Deep Dive, where we keep digging deeper into all these fascinating number sequences from the OEIS, the online encyclopedia of integer sequences. It's really a goldmine if you're into number theory. And today we're gonna tackle sequence A000182.
The tangent numbers.
Tangent numbers, exactly. And, you glance at those first few terms, you get 1, 2, 16, then it jumps to 272, 7936.
It gives you a sense that we're going to be dealing with some pretty quickly growing numbers here.
Oh, yeah. And the name itself, tangent numbers. I mean, right away you're thinking trigonometry.
Well, you'd be right to think so. They actually pop up as coefficients in the exponential generating function for the tangent function.
Right. For those who love a good power series, tan x can be written as, well, the sum over all non-negative integers, n of an plus 1, multiplied by x to the power of 2n plus 1, all divided by 2n plus 1 factorial. It's a pretty elegant connection between a trig function and a sequence of integers.
And if you're familiar with hyperbolic functions, there's a similar exponential generating function involving tan x that also generates this sequence. Though you might have a plus or minus sign difference, it depends on which convention you're using. But the real exciting part about tangent numbers, it goes beyond just trigonometry. They appear in some really unexpected places, particularly in combinatorics.
Yeah, that's the beauty of the OEIS, isn't it? You see these numbers appearing in areas that seems totally unrelated. Like, as a number theory student, you start to see those connections between abstract sequences and, counting things and structures, Makes it a lot more tangible.
Absolutely. Like, take Joyce trees, for example. They're these specific kinds of rooted trees, and the nth tangent number, an, tells you exactly how many Joyce trees there are with 2n1 nodes. It's pretty amazing that a sequence tied to the tangent function can tell us something about the number of these tree structures. It really makes you think about those fundamental principles connecting these seemingly, separate areas.
It really does. And it makes me wonder, what other combinatorial interpretations do these numbers have? I mean, there's got to be more, right?
Oh, there definitely is. Consider tremolo permutations of the set 0, 1, 2. Now, a tremolo in music, it's a rapid, repeating change in intensity, right? Well, a tremolo permutation is similar in a way. It alternates between increasing and decreasing values. And guess what? The nth tangent number, an, counts exactly how many of these up and down permutations exist.
So we're seeing a connection between the tangent function, something analytical, and counting specific patterns in permutations. It's really amazing how these numbers bridge those different mathematical domains.
Precisely. And let's delve a bit deeper into the world of trees. An also represents the number of increasing labeled full binary trees with 2n1 vertices. Full binary means each non-leaf node has two children, left and right, which are considered distinct. Labeled means each vertex has a unique number, usually from 1 to 2n1, and increasing means that the label of a child is always bigger than its parent's label.
Wow, that's a pretty specific set of conditions for a binary tree.
Yeah.
The fact that tangent numbers count these structures suggests a pretty deep connection between how these trees are ordered and how the tangent sequence behaves.
Exactly. And the connections to trees don't stop there. An also counts the number of increasing strict binary trees with 2n1 nodes. If you're curious about the permutations associated with these trees, there's another OEIS sequence, A245894, that dives into that. It's a good reminder that within the OEIS, you often find a whole network of related sequences, each offering a different perspective on the same mathematical idea.
Right. It's almost like these numbers have a secret code that shows up in all these different structures.
Yeah.
It really highlights how interconnected math is, wouldn't you say?
Absolutely. Now let's try a different counting problem. Think about all the permutations of the set 2n. That's just the integers from 1 to 2n. If you insert these numbers in order into a binary search tree, the tangent number an tells you how many of those starting permutations will give you a maximally full binary search tree, meaning the final tree will only have one node with a single child. It's a really specific constraint on the tree's shape, all dictated by the initial order you insert the numbers.
That's fascinating. It's like only certain orderings lead to this almost perfectly balanced tree, and the number of those orderings is given by our tangent numbers.
Exactly. And lastly, in the realm of combinatorics, an also represents the number of standard Young tableaux of a particular skew shape. This shape is created by taking a large partition, n1, n2, 3, 2, and removing a smaller partition, n1, n2, n3, 2, 1. So for those familiar with the representation theory of symmetric groups in Young tableau, this shows a link between tangent numbers and these algebraic structures.
So from counting trees and permutations to these more abstract Young tableau, The tangent numbers are really popping up all over combinatorics.
Hmm.
But it doesn't end there, right? There's got to be connections to other parts of math, too.
You're absolutely right. One elegant connection is to alternating permutations, sometimes called zigzag or up-down permutations. When n is odd, the nth tangent number, remember we're using the OEIS indexing where the first term is A1, equals the number of alternating permutations of the set 1, pay 2. So these are permutations that go up, then down, then up again, and so on.
So it ties back to those tremolo permutations we talked about earlier. This up and down pattern seems to be a common thread when tangent numbers appear in combinatorics.
Exactly. And if we look at the Hankel transform of the tangent number sequence, we see even more structure. For odd n, the Hankel transform of A000182 is the same as the nth term of A000178. Now, the Hankel transform, it's basically a way to create a new sequence from an old one by looking at determinants of matrices formed by its terms. The fact that the Hankel transform of tangent numbers connects to another well-known OEIS sequence, the second numbers or zigzag numbers, suggests a deeper algebraic relationship between the two. Interestingly, the zigzag Hankel transform of A000182 also gives us A000178.
It's amazing how these transforms can reveal hidden connections between sequences, like having a special lens that lets you see the underlying mathematical landscape.
And the connections keep going. Tangent numbers are linked to Euler and Bernoulli polynomials, which are, well, fundamental in number theory and analysis. They also tie into zigzag numbers, those trigonometric functions we saw at the beginning, and even the Fourier transform of a square wave, a concept you find in signal processing. Pretty remarkable how a sequence of integers can connect such diverse areas.
A square wave, huh? That is a surprising connection. Shows you that math can pop up in the most unexpected places.
It certainly does. They even show up in the context of quantum algebras, which are deformations of classical Lie algebras and important in modern physics, and in integrals over n-dimensional hypercubes and green functions. Hodges and Sukumar did some work on that. These connections make you think that maybe the patterns in tangent numbers have applications in all sorts of scientific and mathematical frameworks.
It seems like everywhere you look in math, there's some interaction with these tangent numbers. It's an incredibly intricate web of connections.
And it delves into some pretty advanced areas, too. Tangent numbers are related to the Sheffer-Appel operator calculus, a powerful tool for studying polynomial sequences. They also satisfy a Riccati differential equation, which can be used to generate Meixner-Polychek and Krautchuk orthogonal polynomials. Orthogonal polynomials, as you know, are important in things like approximation theory and numerical analysis.
So these links to operator calculus and differential equations point to a more analytical structure underlying the tangent numbers, wouldn't you say?
Precisely. And there are connections to an elliptic curve, a Weierstrass elliptic function, the Lorentz formal group law, which pops up in algebraic topology and theoretical physics, a Lie infinitesimal generator, and even the Eulerian numbers, which is sequence A00E8292 in the OEIS. Sequence A155585 goes into more detail about these advanced relationships. What all this means is that tangent numbers aren't just some isolated curiosity, they're embedded within this rich tapestry of mathematical structures.
The depth of these connections is really astonishing. It goes way beyond what you might initially think when you see them as coefficients of a simple trig function. A real testament to the unity of mathematics, wouldn't you say?
Definitely. And one final connection along those lines. The absolute values of the alternating sums of the odd-numbered rows of the Eulerian triangle, that's A008292, which tabulates Eulerian numbers, give us the tangent numbers. It's worth noting that the even-numbered rows of this triangle always have alternating sums of 0, so it's this fascinating pattern within another fundamental combinatorial sequence that leads to our tangent numbers.
So the patterns within the Eulerian triangle, which count permutations by their number of ascents, those patterns also hold the secret to our tangent numbers. It's like uncovering hidden relationships between seemingly unrelated combinatorial statistics. Okay, so shifting gears a bit, do these tangent numbers themselves have any interesting properties, maybe in modular arithmetic?
Yes, they do. They exhibit some fascinating modular properties. When considered modulo any odd prime p, the sequence becomes periodic. Now, the length of that smallest repeating block, or the minimal period, depends on the value of p modulo 4. If p is 1 modulo 4, the minimal period is p12. And if p is 3 modulo 4, the minimal period is p1. Knuth and Buchholz proved this back in 1967. This periodicity suggests a deeper algebraic structure at play, especially when viewed through the lens of number theory.
That's really interesting. It's like these numbers have this predictable behavior when you look at remainders after division, hints at some underlying patterns.
Right, and Peter Bala, he's proposed some pretty intriguing conjectures about the periodicity of the sequence modulo any integer k. He suggests that it eventually becomes periodic with a period that divides Euler's totient function of k. He also conjectures some specific Gauss congruences modulo powers of a prime p, specifically that a n pk is congruent to a n pk1 modulo pk. There are some exceptions for the prime p too, but if proven, these conjectures would shed even more light on the intricate structure of tangent numbers.
So even though it might seem like a simple sequence, there's still so much we don't know about it, so many secrets waiting to be uncovered. Let's circle back to how these numbers are defined and generated. We talked about the exponential generating function. Are there other ways to express or calculate these tangent numbers?
Oh, absolutely. There are a handful of important formulas and generating functions connected to them. As we mentioned, the primary exponential generating function is tan x equals the sum from n equals 1 to infinity of an times x to the power of 2n to 1, all divided by 2n to 1 factorial. But there's also a direct link to the Bernoulli numbers, those fundamental numbers that appear in various areas of math. Like number theory and analysis. You can actually express the nth tangent number as an equals 2 to the power of 2n times 2 to the power of 2n minus 1, multiplied by the absolute value of the 10th Bernoulli number, all divided by 2n. This really underscores the interconnectedness of different special number sequences.
So a sequence that starts in trigonometry turns out to be directly related to Bernoulli numbers, which, well, they appear in all sorts of contexts, like power sums and the Riemann-Zeta function.
Yeah.
It's a great example of the unity of mathematics.
Indeed. And there's an asymptotic approximation for A, too, which gives us an idea of how fast the sequence grows as n gets really large. Essentially, an is approximately equal to 2 to the power of 2n plus 1, multiplied by 2n to 1 factorial, all divided by pi to the power of 2n. This shows that the tangent numbers grow extremely quickly, something we already got a hint of from those first few terms.
Yeah, and that fast growth probably contributes to why they appear in so many counting problems, right? The number of combinatorial objects tends to grow very quickly as well.
Exactly. There are other forms of the exponential generating function, too. For example, log sec x is the exponential generating function for an times x to the power of 2n divided by 2n factorial for n greater than 0. And sec squared is the exponential generating function for an plus 1 times x to the power of 2n divided by 2n factorial for n greater than or equal to 0. The appearance of the second function here, well, it further emphasizes the trigonometric roots of this sequence.
So these other generating functions provide different ways of looking at the tangent numbers, which could lead to new properties or relationships.
Right, and there are even continued fraction representations for the exponential generating functions of both tan x and sec squared. Continued fractions often reveal these surprising and elegant properties of functions and the sequences they generate. Paul D. Hanna also came up with an ordinary generating function for the tangent numbers, which provides another avenue for studying the sequence.
Continued fractions, they can sometimes reveal hidden recursive structures within a sequence, can't they? It's another tool we have for understanding these sequences.
Definitely. And you can express tangent numbers using the polylogarithm function and the Riemann-Zeta function, an, and now for n, and a 1, and aim, and a n for n1, zeta 1 to n. These connections to such sophisticated analytical functions highlight how deeply significant tangent numbers are within complex analysis and number theory.
Those are pretty advanced connections linking our sequence to some of the most fundamental objects in mathematics.
Absolutely. And for practical computation, we have a recursive formula. an equals -1 to the power of n1 plus the sum from I equals 1 to n1 of -1 to the power of ni plus 1 times the binomial coefficient 2n1 choose 2i1 times ai. Recurrence relations are incredibly useful for both theoretical analysis and practical calculation.
Recurrence relations give us a way to build the sequence step by step, and often they reveal some underlying structure along the way.
Right. And the exponential generating function ax equals tan x, it satisfies a specific second-order nonlinear differential equation. Ax equals 2ax with initial conditions a0 and a0 and a0. This differential equation leads to a recurrence relation for the aerated sequence 0, 1, 0, 2, 0, 16, 0, 2, 72, where the tangent numbers appear at those odd-indexed positions.
So the differential equation provides another way to define and understand the behavior of the tangent function, and as a result, the tangent numbers. It's amazing how these different mathematical perspectives are all intertwined.
Absolutely. Finally, the nth tangent number can also be expressed as 2 to the power of 2 and a 1, multiplied by the absolute value of the 2 and 1 Euler polynomial evaluated at 0. This connection to Euler polynomials, another important family of polynomials, enriches our understanding even further. And if you want to explore more within the OEIS, tangent numbers are also related to sequence A110501 through the formula AN equals A11105001 n times 4 to the power of n1, all divided by n.
Wow. The more we dig into this, the more connections we find. It really highlights the interconnectedness of mathematics as a whole. So to bring things back down to earth, can we look at a simple example of how these tangent numbers actually appear?
Of course. If we take the Maclaurin series expansion for the tangent function, we get tan x equals x plus 23, x cubed plus 165, x to the 5th plus 27, and so on. You can see right away that the numerators in these terms are the tangent numbers, 1, 2, 16, 272, and so on. This is the most straightforward way they emerge from the tangent function.
That's a really clear demonstration of the sequence. It brings the definition to life,
And as we mentioned before, the third tangent number, A3 equals 16, corresponds to the number of alternating permutations of the set 1, 2, 3, 4, 5. The OEIS entry for A000182 even lists out all 16 of those permutations, showing the combinatorial interpretation in action.
Seeing those permutations written out really helps to grasp the connection between the abstract sequence and the concrete arrangements. It's a great way to understand what these numbers represent.
So, in our deep dive into the tangent numbers, A000182, we've seen that what starts as a sequence of coefficients and a trigonometric function's power series actually turns into this fascinating object with ties to many different areas of math.
Absolutely. We started with their definition through the tangent function, but we quickly uncovered these surprising and really profound connections to combinatorics, where they count things like Joyce trees and alternating permutations.
And the connections didn't stop there. We saw relationships to other fundamental mathematical objects like Bernoulli numbers, Hankel transforms, the Eulerian triangle, and even those advanced concepts from analysis and algebra.
It's truly amazing how a sequence with such a simple starting point can appear in so many different areas of mathematics. Really makes you appreciate the underlying unity of all these different fields.
For those who want to keep exploring, we really encourage you to check out the OEIS sequences we've talked about. A00000111, A000364, A008292, A245894, A155585, and A1100L501, as well as the research we've cited. The OEIS is a living encyclopedia, and each entry is like a gateway to this massive network of mathematical ideas.
And that brings us to our final thought for today. Given the variety of combinatorial interpretations and the elegance of the formulas associated with tangent numbers, what fundamental principle or structure might be at the heart of all these different manifestations? What other connections might be hidden within these numbers just waiting to be discovered? It's a question that speaks to the never-ending journey of mathematical exploration. Thanks for joining us on this deep dive into the tangent numbers.